Hello, AP Chem students, and welcome to topic 3.13, Beer-Lambert's Law. So the learning objective here is 3.13.a, explain the amount of light absorbed by a solution of molecules or ions in relationship to the concentration, path length, and molar absorptivity. So here we go. So the basics of spectrophotometry here. So we'll be using UV vis, just the vis part, spectroscopy in our labs. The older style machines look like this, although this one's not very old, but a lot of you in class, I certainly in class use probeware, which are much smaller. They're more like this size as opposed to these, which take up a whole lot of space on the bench top. In this spectroscopy technique, light at a specific wavelength passes through a solution. The sample itself absorbs some of the incident light, and so you see it like this. So you got a light source, there's some kind of lens, then you got a monochromator. We're going to talk about that in a minute. Your wavelength is selected, passes through a sample solution, which is held in something called a cuvette. Then you have a detector and then your display. The amount of light that's absorbed is related to the concentration of the light absorbing substance in the solution. The detector measures the amount of light that passes through the sample and then compares it to the amount of light that left the source. So we're comparing this amount here versus this amount there. So the instrument can then, so this is related to the concentration. So you can see here we have a lesser concentration, and so we have more light passing through, versus down here we have a greater concentration, and so less light passes through. So then the instrument can give us two measurements, absorbance and transmittance. Those values are related to each other, and on the spectrophotometer you can actually toggle between them. So in AP chemistry, we're going to be using absorbance. But this is that comparison. Again, the difference here is the molar absorptivity and the path length. Okay, so then the Beer-Lambert law says the optimum wavelength value, the optimum wavelength value is impacted by the color of solution. Okay, so just to give you an example here, here's three different dyes. So this would be yellow, red, and blue dye. And you can see that yellow has a maximum absorbance here, okay, which is in the violet range. Red has a maximum absorbance here in the blue range, and blue has a maximum absorbance over here, kind of in the orangish range. So we would set the spectrophotometer to those particular wavelengths of light. Realize that a clear solution would not be able to be studied by spectrophotometry because it's not going to absorb any of the light. And similarly, a cloudy solution will not give good results because the light will bounce off of the particles that are present in that suspension. So that generally when it's cloudy, it's no longer called a solution. We would call it a mixture or suspension or something along those lines, colloid as well. So the Beer-Lambert law allows us to relate these two factors again to each other. The absorbance of light allows us to relate the absorbance of light to the concentration of the solution using this equation here. Okay, so A is absorbance. This kind of E here, that kind of backwards 3 is molar absorptivity. Your B is path length, and your C is concentration. Now, for pretty much every cuvette I've encountered at this level, the path length is almost always 1 centimeter, but that'll be said to you in the problem if you need it. And then, as always, this equation is on the equation sheet. So here's the equation, and then over here we have all of the variables defined. Now, notice that we're studying solutions here, and so this is in the gases, liquids, and solutions portion of the equation sheet. So all of the Unit 3 equations fall here in this section of the equation sheet. So then let's talk about wavelength choice. So in the spectrophotometer, a light source is set at a wavelength by that monochromator that is known to be maximally absorbed by the solution. My pictures are a little off here, but we'll figure it out. This is determined by testing the absorbance of the sample at various wavelengths and selecting the wavelength that produces the maximum absorbance. So I meant for you to be able to see, let me just back up a little bit. I meant for you to be able to see this diagram that we had on the previous slide with the different colors. So there, okay. So we would pick the maximum absorbance, which you kind of heard me talk through before. But you can see here that we can do this study where we have a substance and then we study it at all possible wavelengths, and then we pick the maximum absorbance. So on the exam, if you're asked to pick the best absorbance for a solution, look at this graph and then just go to the top of the peak. So your max. Okay. So then once we've set the spectrophotometer to the ideal wavelength for the solution that we're studying, we can start studying samples to determine the absorbance. So this is a different study. So back on this slide, we're studying all wavelengths, and then here we're setting the wavelength and studying different concentrations of solution. So we begin by testing several samples of known concentration, and we use that data to create a graph of absorbance versus concentration that we call a standard curve. So that might look like this. So if you've got concentration 1, 2, 3, 4, 5 grams per liter, then we would plot those versus absorbance, okay, and you would get this curve. Once we have the standard curve, then we can test an unknown. So if we don't know the concentration of this, we can measure its absorbance. And if the spectrophotometer tells us the absorbance of this is 0.7, then we can use our standard curve to trace over and down to find the value of the concentration of this substance. And that's probably a lab that you're going to do in class. If that's not a lab that you did in class, then there are some virtual labs on this that you can certainly check out. That's it. So what should you be able to do with this? Well, first of all, choose the appropriate wavelength to measure the maximum absorbance of a sample, given a graph of absorbance versus wavelength for that particular sample. Number 2, use a graph of absorbance versus concentration to determine the value of A if you're given concentration or vice versa. Now, this next thing is a fact that I believe I forgot to tell you, but recognize that in a graph of A versus C, the slope of the line is equal to the molar absorptivity times the concentration. So like here, this slope here is that middle portion of Beer's law. So if we go back to Beer's law, right here, if we're graphing absorbance versus concentration, this equation takes the form of y equals mx plus b. Your y-intercept will be 0, because if you have concentration of 0, your absorbance is going to be 0 as well. It's going to pass straight through. So then your absorbance is equal to concentration is going to be the x, and so then your slope here is going to be that molar absorptivity times path length. And then use the equation A is equal to EBC to calculate the concentration of the substance given its concentration, or vice versa, when the path length and molar absorptivity are known. And we have seen before that they give you the graph, and then you need to calculate the slope and know that that's the EB value, and then you can relate the C and the A given that. And that's it. So that is finally the end of Unit 3. It is the longest unit in the AP Chemistry curriculum, if I'm remembering correctly. And I will see you soon to begin Unit 4.